So we just finished a discussion about partial derivatives of functions of several variables and how they really tell us the same kinds of things that ordinary derivatives in single variable calculus tell us. That the x partial derivative of a function of several variables, for example, is what we get by holding all the other variables constant. So taking a slice in a vertical plane with a constant value of y, for example, and then just taking an ordinary derivative of the curve that results from taking that slice out of the graph, right? So all the same interpretations about rates of change, slopes of tangent lines, and all that stuff are still in play for first order partial derivatives. So what happens when I take a derivative of a derivative? So a partial derivative of a partial derivative. We call those the second order partial derivatives. And in single variable calculus, the second derivative of a function, where the first derivative carries information about direction and slope, so increasing versus decreasing versus stationary, the second derivative in single variable calculus carried information about how the derivative changes, and how the derivative changes was reflected in the shape, the bending shape of the graph, the concavity or convexity of the graph of a single variable function. So where a second derivative was positive, we would see a graph that is concave up. So the slopes were increasing, and so we get this sort of a U shape that would collect water if it rained on it, right? And for the second derivative being negative, we get a concave down shape where water would run off of it if it fell down from the sky. And so the question for us in the multivariable context is, can we recover those ideas of concavity when it comes to functions of several variables? And the answer is sort of a complicated yes. Well, let me say it this way. The answer is definitely yes when it comes to taking a single slice at a constant value of x or a constant value of y. Because after all, once we do that, we have an ordinary single variable function whose derivative tells us the slope and whose second derivative tells us the concavity of that slice, concave up or concave down. The problem in functions of several variables is that the concavity in the x direction and the concavity in the y direction don't always tell us a complete picture of the entire concavity of the graph of the function as a two-dimensional surface inside of 3 dimensions. There's a lot other stuff that can kind of happen in between the coordinate axes. And so just the x partial derivative of the x partial derivative and the y partial derivative of the y partial derivative don't tell us the whole story. Instead, we need to pull in one more type of second order partial derivative, which is called a mixed partial derivative. Instead of the x partial of the x partial, a mixed partial derivative would be, for example, the x partial of the y partial, or the y partial derivative of the x partial derivative. Or if I have a function of a bunch more variables, like the w partial derivative of the y partial derivative, the z partial derivative of the s partial derivative. So there's all sorts of more possibilities. More second order derivatives exist than we might otherwise expect. If I have a function of n independent variables, then there is going to be n squared different potential second order partial derivatives for us to compute. And so it's a little bit more challenging to sort of talk about what those mixed partial derivatives tell us about a function. But let's sort of just set the basics of what second order partial derivatives can tell us. So just taking x as my variable for a minute. Right? I want to look at the behavior of my function in just the x direction, so I'm going to treat y as though it's a constant. And when I treat y as though it's a constant, I'm sort of isolating how the output z changes when I change just the input variable x. So y gets held constant and only x is allowed to change. The first derivative in the x direction is then telling me the slope of this tangent line. And so the x partial derivative of that is going to be telling me about how the slopes of these tangent lines change as I change the value of x. So just to go to a dynamic version of this, this picture from the text. So what we're seeing here is a graph of this function of two variables. I've labeled a point where x is 1.75, y is negative 1.5. That's this point labeled right there. And I've also put on there a tangent line in the x direction. So the slope of this tangent line is the x partial derivative. So that slope is minus 0.8 according to this. As well as a tangent line in the y direction. So a constant value of x. This is has a slope which is the y partial derivative. That slope is negative 4.4. And so the x partial derivative of the x partial derivative is giving me information about how that purple slope, which is the x partial derivative, changes as we increase the value of x. So as my value of x increases through this point, what are the slopes doing? It looks like my slopes are getting lesser and lesser and lesser, right? My slope sort of starts out as positive 1.09. I cross through here. It's becoming more negative, more negative, more negative. And so if I take the slice of this three-dimensional graph here with a constant value of y through this point, it looks like that slice is concave down, right? Because my x slopes, as I increase x, are going to be decreasing. And so we would expect that the second derivative of this function, where the second derivative is taken with respect to x both times, so the x partial of the x partial, we would expect to be negative because it's a concave down slice of my graph at that point in the x direction. Whereas in the y direction, if I take the y slice, and that's actually the red curve that's being sketched here, as I increase y through this point, my slopes are, well, let's see, are those increasing or decreasing? I got to try to read those slope numbers. So here the slope is large and negative. It's negative 5.6. But then it's becoming less and less large. It's still negative. But the slopes are getting closer to 0 is another way to look at it. Or geometrically speaking, if I just look at this slice, which is taken in the y direction, in the yz plane, that slice is a concave up slice. And so I would expect the y partial derivative of the y partial derivative to be positive. Where the x partial of the x partial, that would be telling me about the concavity of that trace, that the x partial of the x partial we expect to be negative at that point. So those pure partial derivatives really are telling me about the concavity, concave up or concave down, of the slices that I take parallel to one of the coordinate planes. So just like in single variable calculus. And so the interesting question, or an interesting question that we could ask is, what about the other partial derivatives? Like the x partial of the y partial and the y partial of the x partial. And what might those mixed partial derivatives have to say about any of these questions? So notice that when we were looking before at the concavity of a slice, we were looking at, as we varied the x variable, we were looking at the slope of the purple line, right? And the slope of the purple line were decreasing as we went through this point from smaller values of x to higher values of x. But what if instead of looking at the purple slope, we looked at the green slope at the same time? So what are the slopes of the green lines doing as we cross through this point? That would be asking, how does the green slope, which is a y partial derivative, depend upon changes in the x direction? So we would be looking at the x partial derivative of the y partial derivatives if we're varying x and looking at the green slopes instead. So if I do that, look at my slope here at the beginning, is that smaller values of x is something like, what does that say, negative 3.58. And then as I increase my x value, the slopes of those green lines are going down as I pass through that point. Right? At least it certainly looks like that's what they're doing. And so I would expect that my y partial derivatives are decreasing as I increase x through that point. So the y partial derivative of the x partial derivative should be negative at that point. So it's almost like when I look at the mixed partial derivatives, it's kind of giving me a sense of how this surface, how this graph is twisting at the point in question. Right? Because I'm looking not at how the tangent lines that are parallel to my slice are changing in slope. I'm instead looking at how the tangent lines perpendicular to my slice are varying in their slopes. So we can look at how the green line varies, the y partial varies as I vary the value of x. But I could also do it the other way, right? I could vary the y value and look at how the x partial changes. So if I keep my x value constant at 1.75 in this example, and I vary the y direction, so if I move along this red curve, I can look at how the purple slope changes. And if I do that, as I increase my y value, it looks like my purple slope is also decreasing. It's sort of getting flatter. The authors of our textbook sort of describe this as you lay a pencil down on top of this curve, right, perpendicular to my curve, and as I move along this curve, sort of look at what the slopes of my tangent lines are doing. So these slopes start out at about negative 0.8, and they get closer to 0, the purple slopes do, as we increase the value of y. And so one interesting thing about this is it looks like both the y partial derivative of the x partial derivative, which was the rate of change of these green slopes as we pass through this point, and also the x partial derivative of the y partial derivatives, which is the slope of, the y partial of the x partial, which is the rate of change of the purple slopes. Both of those look like they're negative at the point that we're interested in here. And that's actually not an accident. And this is both, I guess this is really good news for partial derivatives. And it's that whenever we have a function that is sufficiently nice and well behaved, as long as my partial derivative functions are continuous in a neighborhood of the point in question, then every mixed partial derivative is going to be equal to every other mixed partial derivative with the same subscripts. Right? So the x partial of the y partial and the y partial of the x partial are going to agree with one another. Their values are going to be the same as long as those second partial derivatives are continuous in a neighborhood of the point in question, which is almost always the case for the functions we study in a safe space calculus classroom. Again, real analysis, you might push that boundary a little bit later on. But for the purposes of our course, we're not going to see an example where this doesn't happen. So that's part of the good news too, is that even though there can be, for a function of n variables, there would be n squared minus n over 2 different mixed partial derivatives that we could compute on the second order. N squared minus n of them, that those are going to be equal in pairs. So the x partial of the y partial is the same as the y partial of the x partial. The x partial of the z partial is going to be equal to the z partial of the x partial. And so I can rearrange the order of these subscripts however I like to. As long as those partial derivatives are continuous, they're going to agree with one another. So I don't have to compute fxy and fyx separately. As soon as I compute one of them, I'll be done, because the other one's going to be equal to it. Which means that if one of them seems easy to compute and the other one seems hard, compute the easy one, and then the hard one's going to be equal to it. So that's the other sort of good news, is that even though these mixed partial derivatives are sort of challenging in an interpretive context, in a computational context, they're really not that bad. We only have to compute half of them, if you like. So what we're going to see as we move into the next couple of classes is tomorrow we're going to get vectors into the mix. So how can vectors help us to understand the first order partial derivatives? And then as we get into Thursday, we're going to think about how to bring all the different second order partial derivative information for a function together to determine whether a multivariable function has a local maximum or a local minimum near a certain point, right? In other words, when are we going to be able to trust that not only is the x slice and the y slice concave down at a local maximum, for example, but how are we going to know that every other slice that we could take is also concave down at that point? If it really is a local maximum, every single one of its slices needs to be concave down at that top of the mountain. Or similarly for the bottom of a valley, right? Every single slice would need to be concave up. But the pure partial derivatives only tell us about the two slices through the x and the y direction, right? So in order to get the full sense of that picture, we need an entity that's able to tell us that what is the concavity of every slice? Do all the concavities agree, or are some of them going to be opposite to others? So where the first derivative is actually going to be a vector quantity, as we'll see tomorrow, the second derivative, is actually something even more fun. It is a 2x2 matrix, or it is a linear transformation. Those of you taking linear algebra with me this summer, this is probably, for me, the most profound place where the linear algebra and multivariable calculus really cross streams when we think about second order partial derivatives and what information that they carry and how we extract that information from what's called the second derivative, sometimes called the Hessian of a multivariable function. And we sort of get in multivariable calculus some black box formulas that we don't really understand why they work. But in linear algebra, we can kind of justify why it is that those things work the way that they do. So tomorrow is all about derivatives in a vector context. And then the day after, we're going to look at optimization problems. How do I find the tops of hills and bottoms of valleys? First of all, in an unconstrained setting, and second of all, in a constrained optimization setting, where instead of looking at the entire graph, we're just looking at some slices of the graph because we have some constraints on our independent variables. So that's going to be the story for the end of the week for us.